Okay, so what we will be starting with is notations and mathematical induction. So the most important notation or mathematical language you need to know, especially given the fact that you'll be doing counting, is the set theory. So you need to know about basic notions of sets, being an union, intersections, being an element of, and so on. So I will call this first thing is about sets. Okay. So the terminology with sets or notation you probably are familiar with. Just a set is say a collection of elements. If a set, say A, consists of elements, this is like to get you A1, A2, AN, then we write, say A is equal to, so use this bracket notion, say A1, A2, AN. Okay, so this is the common way to write a set with, say, n elements. Sometimes we also use Venn diagrams and so on, but this is essentially the common notation I will be using. So a set consists of, say, 1 through 3, 5, 7, can be written as say B 1, 3, 5, 7. But also you can express this set sometimes as with a description or by describing elements. Say you can say B is all the say numbers which looks like 2k plus 1, where k is either 0, 1, 2, or 3. This is a descriptive way of explaining a set. It's the same set, but instead of saying that listing the elements of B, we give a sort of description of elements with some condition on the right-hand side. So this bar and this notation is it's called describing a set by description notation. There's many different forms of it, and for example, you could be using so say positive real numbers. Can be described as so this could be a set C. Sometimes notation is actually this, positive real numbers. This could be described as all real numbers which are because it's positive, we don't want 0, like this. So now I describe them by giving an inequality. Here I describe them by giving possible values of k. So you can actually say it's all real numbers, where R is the real numbers. R is the set of all real numbers. So there is actually mathematics called model theory, which discusses these descriptions and definability and so on. They ask very, very fundamental questions and do mathematics of these definability. But the set is defined this way. You can define sets in different ways. There's no terminology that comes with this. Like you call a set finite set if it has finite many elements. So for example, here B is a finite set. When it's a finite set, it has a finite many elements. You can talk about number of elements in it. Okay? So when you have a finite set, the number of elements of B is denoted by these two lines in B. Okay, so you put two lines. So what is two lines of B in this case? What? 1?
1, 3, 5, 7.
No, number of elements in B.
4.
4. So 2 bar B is equal to 4. It's just the number of elements in B. Okay. So when a set has infinitely many elements, then it is called an infinite set, right? We sometimes use the infinite notation. We sometimes write I actually don't remember this used too much, but we can write that it has infinite. But essentially, we will not be dealing with infinite sets that much. But this is finite sets, and this is the notation. We'll use this quite a bit. Like some point in the course context, I said we have an inclusion-exclusion principle. Let me go back to that. Remember this inclusion-exclusion principle. So the formula will be expressed like this. I, 2 bar, is equal to sum AI plus blah, blah. So we'll be using this bar notation, like 2 lines for writing formulas. Okay, that's why you're learning it. So 2 lines will always means number of elements in a set. Okay, and it will appear in formulas. Another thing that appears in these formulas is the sigma notation, which I will come to that too. But so this is the 2 bar. I don't know. Also, you saw in this formula. Okay, in this formula, which I will describe later, we use this thing, we use this thing, and we use this thing. So the bar you just learned, this thing is union, this thing is sigma, so you'll have to learn that too. Now this kind of things that commonly used by mathematicians, notations that we always use, I will introduce them one by one, so that you know what I'm saying. So we use the notation A is a member of A to mean A is an element of Big A. Here you also see that a mathematical custom that when you write a set, you use big capital letters. And when you write its elements, you use small letters. These are all embedded inside the culture. So like one could be writing this too. But you will find this, as a mathematician, you find this very awkward. That's why we don't use it. But there's nothing against using this, right? You could use a small letter for a set. You could have used a big B for one of its members. There's no reason that they should be all same. There's no reason they should be small. But still we do this way, okay? It's just a culture. So anytime we write a set, we'll always use a capital letter. And when we talk about its members, we'll use small letters, and we'll use same letter as much as we can. Okay? So these things, just comes from like 15th century. Some person wrote it that way, so we have to use that way. So if A is not in A, then we write, usually you put a line to say something is not true. So if equality, say 5, 3, you put a line, they're not equal. Okay? So this line negates what you just wrote. So this negates it. Okay, so if every element of A is in B, then we say A is a subset of B, and write A is a subset of B. So this is the notation for being subset. Now, here it comes the Venn diagrams. So A is this set, B is this set. So subset means it's completely inside B. These are the diagrams you draw. They're called Venn diagrams. This becomes useful when you talk about unions, intersections, and so on. So it means every element in A is also in B. Okay? This is something that you should also know. A in B is if and only if. This is the sign for if and only if. So that means equivalent statement. Okay? Means that A is in A implies A is in B. And this is implies. So these logical notations and signs also may appear a couple of times and use. So this means A is in A implies A is in B. So this is equivalent to this. Okay? There's actually a small section on logic in this course, but we'll see how much we can do it when it comes. I often do it in 132, but we skip it in 110. That's the idea. So these kind of things, if you want to get more familiar with them, you can open Grimaldi. There's 2 sections there about logic, and you can read them. But essentially, this is how much I'll be using for this course. So set theory is this funny thing called universal set. So this is a set is said to be a universal set if it contains all the other sets. So a universal set is like your framework where you work in. Okay? So it's usually denoted by this U, and all the sets you talk about will be inside it. Okay? I'll tell you a few words about it, why we need that in a few minutes. But because now we consider everything inside the universal set, we can talk about unions, intersections in a very easy way that allows us to introduce these notations. So, given 2 sets A and B, we can talk about the intersection or union this way. So this will be all the things in the U. So why should I write to express union? So it's the description of things. which are in the union. So what is the description of things in the union? How can I write a union? What is to be a member of union?
X is an element of A,
Uh-huh.
and or is an element of B.
And or? Huh?
And it's both.
And or? Or. Uh-huh. So or is the one that we need to use, right? Yeah, either that or this. And the intersection is close. We don't even use the universal set for that. We could have used A as well. But how do you write the description of things in the intersection? And, with and, right? So X is in A and X is in B. So these are terminology notation. Sometimes you use A complement. This is the things that is not in A. Sometimes people use bar as well. The differences. Huh? Yeah. Not in there. You can talk about difference of two sets. This notation is not standard, but you can write it A in A, where A is not in B. Like this. There's a symmetric difference. Does anybody know the symmetric difference? So it's this. So this is A, this is B. So this is this set. Can you tell me which set is that in terms of description?
Difference between the union.
So you could actually directly write it as union minus intersection, which uses all the things we just introduced. Or you can say that X is in A exclusive OR. Do you know exclusive ORs? Did you learn it? It's an OR which is not true when AND is true. There's a notation for it, but it's called exclusive OR. Sometimes, but I mean, and the best way to say is X is union and X is not in the intersection. But there is something called exclusive OR, and it completely fits into this symmetric difference. So this is symmetric difference, which we have here. This is intersection, and union is everything. Complement is the rest of the set. You can draw Venn diagrams to explain all the sets. We sometimes ask questions that involves these in a sort of funny way. So why you need universal set? So think about this question. So there is nothing preventing member the sets being an element of a set. So think of like you could be making a list in to put in front of your fridge. So you can make a list of groceries that you want to buy. Tomatoes and so on. So you can make a list of groceries. You could make a list of things to do. So think such as list, like. But sometimes you could be tempted to do list of lists, right? List of lists that you don't like. Like this list you don't like because it tells you things you have to do. It's kind of annoying things. Things that annoys you. Like list of things that you don't like. You can make a list of things you don't like. But, I mean, if you start making list of lists, there's nothing preventing you to talk about list of lists that doesn't include themselves in the list. Okay? It's not a leader. Yeah, just think about it. This list has list of groceries. So it's possible that this can appear inside other list, right? So that means there's nothing preventing trying to talk about list of lists that does not have itself in the list. I mean, you can talk about list of lists where you can put a list in there, so you can put itself in there too, right? Why not? Since you're making list of lists, itself can be in there in the list. But then you get into this kind of questions. You can make a list of lists, right? So let's try to make a list of lists. This is exactly that question. That does not have itself in it. So let's try to make this list. So you are making list of tomatoes and vegetables you need to buy. You're making list of things to do. You're making list of lists that you don't like. So why not let's do a list of lists that doesn't have itself in it. And now you can ask the same question that I asked in set theory. Is this list in this list? It became a little funny one. Is this list is in the list? So can I put this list into this list as one of them? So can I say A is a member of A? Think about it. This is discussion in logic and set theory. So I'll bring a board and try to argue one way, convince you that it's wrong way, and then argue other way and convince you that it's wrong too. So it's a very fun paradox. It's called a paradox. It's actually Russell's paradox. It's called the Russell's paradox. So suppose A is in A. That means this list is in your list. Okay? Suppose that this is in the list. But it's a list of lists that does not include itself in it. As soon as you put it there, it violates its definition. Its description was a list of lists that doesn't include itself in the list. You cannot put it there. It will violate that. Right? So that means it should not have it. Right? It cannot be there. Suppose let's not put it. So let's not put this in there. So suppose you don't put it there. But then your list does not include itself in it. So your list becomes a list that does not include itself, which means you have to put it. If it is not there, suddenly your list becomes a list that does not include itself, so it has to be there. So now you have to put it. In either way, you're in trouble. You put it, problem. You don't put it, problem. This is called a paradox. And Russell's paradox is called. I don't know how it's written, but so it's a very, very well-known paradox in set theory. So a couple of fixes came up in. This is maybe above the level of this course, but I just wanted to explain to you, set theory is not as simple as it looks. So some really big people, big thinkers, thought about these things and came up with some problems that can happen if you don't carefully lay things down. So paradoxes are things like, there is a famous paradox by Zeno. When you listen to it, you're like, oh, he's right. I mean, this is something, a big problem. But then in real life, you see it's not a problem. Right? Like Zeno's paradox in Calculus. Have you heard about it in Calculus, Zeno's paradox? This has nothing to do with what I'm talking about, but it's also a nice paradox. Zeno says that, actually he challenged someone, said with an arrow, said, if you take your arrow, point it towards me, and throw it to me, it will never reach to me. Zeno is there, like Zeno, and then the arrow guy. And this is the distance between them. And he throws his arrow. We know from daily experiences that that arrow will hit Zeno and kill him, right? And so sure we know this. But Zeno says, it will not reach to me. And his argument is so convincing that I'll tell you now. That's why it's called a paradox. Zeno says that this arrow first has to travel half of the distance between us to reach to me. It first has to travel half of the distance between us. And he's right. It has to travel half of the distance. Right? As we know that. And then once it reaches here, that arrow has to travel half of the remaining distance to reach to me. And that's correct too. We know from experience, once you reach half, you need to go more half. Once it reaches this point, Zeno says, the arrow has to travel half of the remaining distance. That's also true, we know that. And he says, then it has to travel half of the remaining distance. And then half of the remaining distance. And then half of the remaining distance. So he says, it will never reach to me. It always has to be travel half of the remaining distance. So he's right, right? Why is that right? Anybody can disargue this argument, beautiful Zeno argument? How come it reaches to you when you have infinitely many small steps you have to take? Think about it. I mean, you don't have to know everything. It takes time to think about these things. I mean, it took centuries for people to digest this. Right. So sometimes infinite sequences looks like mathematical funniness, but when you think about it, it's exactly why it reaches to you, that sum is 1. So anyway, I mean, part of the thing is that, of course, the arrow doesn't use as 1 second for each of these halves. The time that required to take these smaller pieces gets also smaller and smaller. So that's why it can reach to them, okay? But these are called paradoxes, and a lot of mathematics goes into this. I mean, people told centuries about this to figure out how to set these things right. Anyway, the universal set comes because of the requirements of set theory. Without that, you get problem. Okay. There's a big guy called Gödel. He's actually one of the biggest thinkers of this century. I think he he was a very good friends with Einstein. And in the Advanced Institute, they took walks and so on. But sadly, he was a little bit concerned with his diet, and he didn't eat much towards the end of his life. He essentially killed himself by not eating. But he was a very big thinker, and he was a very close friend to Einstein. So he was the one who thought about these things also. There's a theorem called Gödel's incompleteness theorem. It's a very, very nice theorem. These things are deep mathematics goes into, but some of these things found their ways into engineering later. So just to know that. Okay, so where are we? There is anything I introduce or talk about, there's usually 4 or 5 hours of material and very deep mathematics behind them. But we will be only talk about some surface things. So sigma notation. This is another thing I mentioned that you will be using in inclusion-exclusion principle. Remember that inclusion-exclusion principle look like this. Some set with elements 1 to n. You have equals to sigma 1 to n ai minus. It's a big formula. There's more things involved. But actually, I can say ij plus and so on. So you've seen the unions. You've seen the intersections. You've seen this. So now we'll see that this thing. This is called sigma notation, and that's extremely useful notation. Most of you probably seen it in engineering courses so far. It's a compact way of writing sums. So if, say, x is a sum of, let's say this is a sum of numbers a1 to an. It could be, say, a k, say a4, a10. Then we write, so meaning, let me write this. S is like this, a1, a2, a10. So if it's sum of these numbers, then we write this. We say S is equal to sum I 1 to 10 AI. Okay? So this is the notation. It's just a notation. It doesn't have any mathematics in it, just a way of writing. So anytime you see this, you say this is equal to that. That's all you need to know. Okay? So this lower part shows where it starts, and this top part shows where it ends. Sometimes, of course, you could start with a, say, 3. It could be like this. It doesn't have to obey the indexing strictly like that. So you could have this too. I think in calculus you use sigma notation quite a bit, right? So you know this. So any questions so far? Anything? So how many people knew about paradoxes? Russell paradox. Anybody knows Russell paradox? Yeah? So is there, if you, I was teaching calculus last year, and I haven't taught calculus for such a long time. So I couldn't remember some of these history. So I looked at YouTube. YouTube has so many calculus videos, unbelievable, like thousands of videos. Some of these MIT videos, and some like people just lectures from different schools and so on. So after a while, like you can find hours of material to read and to watch. And there are some mathematics videos too, just talk about Gödel, talk about paradoxes. So if you ever want to know more about them, just go to YouTube. I mean, in case I can also sometimes find a video and share with you over the email. Like I used to do that every week with them. If you're interested, I can send you videos. I actually send them funny videos too, but after a while, it just the course got too serious, so they didn't want to hear anything. But there is lots of videos. So if you're bored one day, just check them out. So one thing we need to know, this notation, sigma notation, you can play with the indexing. For example, suppose that you have a sum. Say, suppose you have this sum I0 to 5 xi plus 2. This is a valid notation, right? 0 to 5 xi plus 2. And we know how to write this. We can write this saying that this is x2 plus x3 plus x4, x5, x6, x7. When you reach to 5, you stop. We know this. We can write it that way. But then as soon as you see this, you say, okay, I can write this again with sigma j 2 to 7 xj. Just using another letter, j. But each time when you need to do this change, you want to do this without using this middle line. You want to pass from here to here directly. So this is called an operation. This is called a sort of sigma notation operation. What we did to pass from here to here, can you tell me what happened? What we did to go from there to there?
Reduce the size by two, increase the interval boundaries.
We can also say we decided that we can introduce a new letter called I plus 2. And then we can say I0 is same as j equals 2, I5 is same as j equals 7. So basically you replace all the I plus 2's with j. Okay? This is a very simple trick, but it's extremely useful. I'll show you how useful it is in one example. This basic trick gives you everything you want. So this is an example. Suppose we want to know this sum. Formula means compact formula, so you can't just say this is already a formula, right? We want to find some compacting. It doesn't involve dots. So here is the trick that you do. I mean, since I want to explain how this can be useful, I will be solving this myself. But these kind of things we can also decide to solve. So this is the trick that you do. First, you write it in sigma notation. So this is your S. If I wanted to write in sigma notation, what should I do? How should I write this in a sigma notation? I from 1 to n, and inside I, you could use n too. Okay, so we wrote it in sigma. That doesn't give us anything, right? Okay, so let's do one more step. I will write this as difference of two things. Right? So it's a very actually simple exercise to see that this is equal to this. Right? Does everybody sees that? Just make the bases equal and you'll see that the top will be just 1. But then sigma is sum of things. But if you're summing things which are already differences, you can sort of distribute the sigma over your expression. Which means you can write this as sigma minus sigma. Like this. So I have two sigmas now. One sigma here, one sigma here. I haven't done anything, just wrote it as two sigmas. Okay? Now, this starts with 1, goes to n. This starts with 2 and goes to n plus 1. So they're not really tracing the same things. So why not make them trace the same things? So this thing has a 1 in it. So let's take that 1 out. Look at the rest. Okay? This is the first part. The other one has an extra n. And that's n plus 1 at the end. Let's keep it separately. Look at the rest of it. The rest of it is sum I1 to n, 1 I plus 1. No, it goes to n. It doesn't change. I haven't changed the n yet. So I just, oops, sorry, n minus 1. You're right, I think, sorry. So I took the n out, okay? Anybody who can follow, just ask. You can stop and look at it. Can you follow it so far? I can go very fast sometimes. You have to slow me down. This is the only way you can follow sometimes. Okay, so we are game here, square. So we haven't done anything. We haven't calculated anything. So let's do the trick that I just mentioned. So the trick that I just mentioned said that when you see something like this, you can replace it with j and change the indices. So I see something like that. I see like I plus 1 there. So I can replace it with j. Okay? So I will be declaring a new variable j as I plus 1. Okay? That's all I'm going to do. So that's equal to 1 plus sum I2 to n, 1 over I. So this is still here. Now, when you put j there, you get 1 over j. Sum. The sigma inside is 1 plus j, but the limit has to change. So what are our new limit values? What are our new limit values? J becomes 2 to n. Okay. Now, this is minus. Now let's look at it. I have 1 plus a sigma, 1 over I, minus another sigma, 1 over j's, and then 1 plus n. But this sigma and this sigma are identical except this variable. But variable doesn't mean anything, right? You're just using it to express your sum. So can we say these are same things? So if this sum is like t, this sum will be also t. Can everyone confirm that? So actually you just get this. 1 plus t minus t plus 1 over n plus 1. So t's cancel. So the answer is this. Okay. Now, this is probably a very bulky way of doing a very simple calculation that you could have done. This way. You can just write this as just a sum, one like this. And then summing up on the left hand side is S. On the right hand side, you just get these cancellations. So you get 1 minus. This is exactly what we did. There's nothing more than that. But we did it in such a way that we use the sigma notation. Unfortunately, this is more common in mathematics or in like when you're doing things, you'll be using this more common. We'll be using this throughout the course. This kind of switches, cancellations, and sigmas, and so on. So this is more common than this kind of writing it down, okay? So you need to learn this. I want you to learn this, okay? Think about this. Try to digest it, understand it, and you may need to use this trick many times. So see you on Tuesday. This is all today.